We're going to start off today by doing two multiple choice questions. It's multiple choice 3 and 4 from your worksheet booklet. I would like you to enter the answers to multiple choice 3 and 4 into the slot for multiple choice 1 and 2 on your responder, please. So multiple choice 3 and 4 in your worksheet booklet. Enter it, please, in multiple choice 1 and 2. When you finish that, click Submit. If you don't have a phone, then just get your neighbor to enter it for you and click Submit. We'll give you a few minutes to work on that. We'll see what results we get, and then we'll take a look at another question. All right, let's take a look at these here now. If we go with the statistics that we got from your group, you guys actually almost all got both questions correct, and that's fantastic. But I want to actually point out a couple of things that the other classes messed up on for a couple of reasons. One, just in case you guys do end up messing up on that same thing at some point. But number two, so that if anybody goes back to watch this tonight, they can take a look at the common mistakes. Not the common mistakes for you, because you guys are too smart, but the common mistakes for most people, for normal people, just not for you guys. Okay, number 3 says in an automobile collision, the severity of injury to the driver can be reduced by an airbag. In a car initially traveling at 100 kilometers per hour, right away, we want to draw attention to that kilometers per hour because we want to convert that to meters per second. Okay, if we circle that in red, we're more likely to remember to do that conversion. We may remember anyways. Okay, we may remember anyways to do the conversion, but we're more likely if we see it circled or highlighted or something. 62 kilogram car in 90 milliseconds. Again, another strange set of units that we don't normally see. Set of units that we can't use when we're plugging it into an equation. Want to find the average force. Let's circle our actual givens here now. This is going to be VI. Okay, this is going to be the mass. This is going to be the time. We're looking for the force. If we read between the lines, there is actually one other thing that we have given to us here. What is it? Yep. Good. VF is what? Good. If it stops, VF is going to be 0 meters per second. All right? We know we're going to use impulse to solve this question, clearly, since pretty much everybody in this class got it right. Why do we use impulse, though? Besides the fact that that's what we've been doing the last couple of days, and I'm probably going to give you a question on impulse. If you see this 3 months from now, why would you use impulse to solve it? Time and force. See that in the same problem? We're going to use impulse. Now, impulse is equal to F times T, and it's also equal to M times delta V. Now, it's only these two parts of the equation that appear on your data sheet, but that's okay in this case because that's the only two parts that you're going to use. You're going to end up rearranging this to solve for force. You get M delta V over T. The mass is 62 kilograms. The change in velocity is 100 kilometers per hour minus 0, but we have to convert that kilometers per hour to meters per second. And we remember that because we've circled it or highlighted it to draw attention to it. How do you convert 100 kilometers per hour to meters per second? Divide by 3.6. And again, I'm getting 27.7777. The final velocity would actually be 0. So it's 0 minus 27.7777. The time is 90 milliseconds. If you take a look at your data sheet, page 2, there's a section right in the middle of that, page 2, that says SI conversions or SI prefixes or something like that. Prefixes used as SI units. Look for an M for a milli. It says 10 to the minus 3. So we're going to make this 90 milliseconds, 90 times 10 to the minus 3 seconds. Or you can just divide it by 1,000 either way, and it works. Do the math there. We end up getting negative 1.9 times 10 to the 4. But since they only ask me for the magnitude, I can drop the negative. That's fine. Now, in the other two classes, we actually had a fair number of people, about 25% actually, choosing option A, which is incorrect. But it was funny to me, not funny, but it seemed odd to me that about a quarter of the class in both classes got it wrong. And in both classes, it was A. Everybody that got it wrong picked A. What do you think happened there? What's your guess? Why did so many people pick A, the incorrect answer? Yep, they used 100 kilometers per hour. They forgot to convert 100 kilometers per hour to meters per second. So you can see that's a pretty common mistake. Okay, none of you guys made that mistake here today. That's good. But let's still continue to draw attention to it with a red circle or a pink highlighter or whatever so that we don't forget to do it down the road. Number 4, you guys all said the answer was B. That's correct. It's kilograms meters per second. I wouldn't memorize that if I was you. Okay, I'd go back to my equation for momentum, and I can use that because impulse is just a change in momentum. From that, I get kilograms times meters per second. Mass kilograms, velocity meters per second. Done. Done. Now, in the other classes, one of them, about 25%, said D. In the other class, about 20% said D. It's easy to get those mixed up, right? Kilograms meters per second squared. D's wrong. Okay, if we look at the equation, it's quite clear that it's kilograms meters per second. Kilograms meters per second squared comes from force. M is kilograms. Acceleration is meters per second squared. So if you wanted to find the units for force, well, we could say it's kilograms meters per second squared, but not for impulse or momentum. Good? All right, I'd like you to take a look at one more, please. You're going to submit this as numerical response number 1. Okay, submit it as numerical response number 1 on that responder sheet. All right, everyone, let's take a look at number 5 now. We got most people's responses here, and the vast majority of them are correct. The answer is 1.94. Now, there were a couple people that were unsure of what to do here. One person said they didn't know what the answer was. Another person said the answer was, looks like they changed it, actually. We had another answer earlier that was 0 point something. It looks like it got changed to 1.94. That's good. Okay, let's take a look at it here. You guys are doing fantastic on these today. Let's take a look at it just for the one person who wasn't sure and then a couple people that didn't respond to it. It says a full draw is the maximum distance that an archer can pull back an arrow. Using the recurve bow shown below, a particular archer requires an average force of 130 newtons. That's going to be my force. To pull full draw, 70 centimeters. That's going to be a distance, or a displacement, but we have to be careful here because we're dealing with centimeters, not meters, and we want to be meters, right? Now, one little aside here. When you pull back the string on a bow, the force is not a constant value of force. The force changes. The further you pull it back, the bigger the force gets. Right? It's just like an elastic. When you pull it back further and further and further, by Hooke's law, the force becomes bigger and bigger and bigger. That's the case here as well, but they're simplifying the question by telling us the average force is 130 newtons. That allows us to use the impulse equation if we have to, and to put a value of F in there. Okay, if we have all these different forces, we can't put them in the impulse equation. If we have the average of all the different forces, we can. We can put that average in there. All right, what else we got? We get an arrow that has a mass of 20.6 grams. Circle that grams because we want to convert that to kilograms. When released from full draw, it's moving at 94 meters per second. That's going to be a speed, right, or a velocity. Can you tell me what velocity it is? VI, VF? When it's released. Okay, pull back that bow. Let it go. How fast is it moving right now? 0, good. When I let it go, how fast is it moving? 94, right? So what is this, VI or VF? This is going to be VF. In fact, VI is going to be what? 0 meters per second, good. We're looking for the impulse here. Clearly, we're going to use impulse here because it asks us for the amount of impulse. We're going to say that delta P is equal to F times T, and it's equal to M times delta V. This time we're going to use these two parts of the equation. We have the force, but we don't know what the time is. Okay, let's multiply M times delta V to get delta P. It's 20.6 times 10 to the minus 3, or you could say 0.0206 kilograms. Either way works. Times 94 meters per second minus 0 meters per second, the final minus the initial velocity. When we do that, we get 1.94 Newton seconds, or 1.94 kilograms meters per second. Now, what a few people did, not a ton, but what a few people did in the other classes was go ahead and divide that by the time. By the force, 130 newtons. I think people thought, since I'm given force, I have to use it. Well, in this case, the force is irrelevant, right? If you divide that by force, what do you end up getting? If you divide the impulse, delta P, by force, what is that? Yeah, it's the time. So when people took that number, 1.94, divided it by the 130 newtons and got the value, whatever they got, what they were solving for was not wrong, but it wasn't what we were looking for. It was the time. Does that make sense? Good. We're going to spend a few minutes here right now going over some new stuff, but not a great deal of time. We'll take about 15 minutes at the end of class to drop those eggs from yesterday. Take a look up here right now, guys, please. This is a bit of an extension of what we started 2 days ago and then what we did with the activity yesterday. There are mathematical aspects of impulse that we have to be aware of and that we have to be comfortable with. In fact, clearly, when we look at how you guys did on those 3 questions that I just gave you, you are comfortable with it. Okay, you're doing a good job on the mathematics of it already, a very good job on it. But we also have to be aware of the qualitative implications of impulse, things that impulse can explain. Okay, if you talk to your 8-year-old brother or sister, okay, they might ask about something that they see out there in the real world. They might say, how does that work? Why does that do this? Or whatever the case may be. Okay? They may not be able to understand the explanation, but they have a better chance at understanding the qualitative explanation than they do the mathematics. There are things that we can explain qualitatively with physics as well, not just mathematically. There are a couple of big scenarios that we explain qualitatively with impulse. The first one is one that we talked about yesterday and the day before. The first one is when we have what I call a predetermined impulse. A predetermined impulse is an impulse whose value is already determined by the initial conditions of the object. For instance, a car is traveling down the road at 100 kilometers per hour. It will stop. At some point, it will stop. It might be an hour from now. It might be a minute from now. It might hit a concrete wall. It might come to a gradual stop at a stop sign. It might hit another car. Whatever. It doesn't matter. The impulse of that car is determined by how fast it's moving and what its mass is. We know what its impulse will be as it's driving down the road. We know what its impulse is going to be no matter how it comes to a stop. Its impulse is predetermined. We can't affect it. We can't change it. Its impulse is what it is. Typically, that occurs when we're stopping objects, stopping a car, stopping a baseball, right? You catch it. We talked about this the other day. You catch it and you cradle the baseball as opposed to just stick your arm out and rigidly stop the baseball. An airbag stops your head. What cushions your head? But the impulse experienced by your head is going to be the same no matter what, no matter how it comes to a stop, whether it hits the windshield or whether it hits the airbag. When we have a predetermined impulse, typically the thing that we want to do is increase the stopping time. The airbag increases the stopping time of your head over the windshield. The baseball glove increases the stopping time of the ball over just your bare hand. The brakes increase the stopping time of the car over the concrete wall. Usually you want to increase the stopping time. What effect does that have? Well, it has no effect on the impulse. But the effect that it has on the force is to decrease the force. And that results typically in less injury. We've talked about a number of different scenarios that can be explained by this whole idea of predetermined impulse. There's a million more that we haven't talked about and that we won't talk about. There's a very good chance on your unit test and on your diploma exam that you will get a question that talks about predetermined impulse. It probably won't use those words. It'll probably be in the context of some kind of impact cushioning thing, some kind of safety thing. Regardless of what it is, whether it's the airbag or the car stopping at the stop sign, or whether it's bending your knees when you jump off a desk, or whether it's cradling the ball as you catch it, doesn't matter what it is. The answer is increase the stopping time, decrease the force. Okay, whatever that question is, that's the answer right there. Now, the other implication that can be explained by impulse is when we have what I call a non-predetermined impulse. I don't even think that's a word. I don't think you can hyphenate a word twice, right? Doesn't matter. I'm going to say it is a word. And if you don't like it, too bad. when we have a non-predetermined impulse. That occurs when you can affect the impulse of the ball. You can change the impulse of the ball. Typically that occurs, or the object, whatever it is, typically that occurs when you're causing an object to start moving, not to stop moving. An example of that would be a golf ball sitting on a tee. Okay? It's sitting there with zero momentum. If you're a bad golfer, you might give that golf ball just the tiniest bit of momentum, and the ball ends up going very, very slow and goes 6 feet. If you're a good golfer, you might give that ball a lot of momentum, and the ball travels 280 yards. Okay, you affect the impulse experienced by the ball. It's not predetermined at all. You control it. Now, there are two ways that you can control the impulse that the ball obtains. Number one, you could hit it harder. Okay, intuitively, we know that if we hit the golf ball harder, or if we hit the baseball harder, the guys that can hit home runs in Major League Baseball, generally they tend to be strong. Okay? Why? Well, because that allows them to hit the ball harder with a bigger force. If you give it a bigger force, you're going to increase the impulse experienced by the ball, and it's going to go faster and farther as a result of that. So we can increase the force. But the other thing that we can do when we're golfing or hitting a baseball is have good form. When you swing a golf club, you don't swing a golf club like this and then stop as soon as you hit the ball. You've already hit the ball. What difference does it make? When you're swinging a baseball bat, you don't swing the bat and then stop swinging as soon as you hit the ball. But you've already hit it, so what difference does it make? What do you do, Riley, by the way, when you're swinging a baseball bat? After you hit the ball, you follow through, right? And that's probably really, really bad form when I just demonstrated. But bottom line is I showed you that we follow through, right? Whether you're hitting a golf ball or a baseball or anything else for that matter, a tennis ball, why do you follow through? It doesn't increase the force on the ball. It increases the time of contact. In the first scenario, we increase the time of contact. It decreases the force because the impulse remained constant. In the second case, we increase the force or the time of contact. We're actually going to increase the impulse. And that's going to make the thing go farther and faster because it has more impulse. So you want to hit that ball hard. You want to make that ball go fast and far. Do two things. Hit it hard and have good form. Follow through so that the ball is in contact with the bat or the club or the racket for a longer period of time. Make sense? All right, I'm going to show you a couple fairly short videos just to explain and to demonstrate these things that we've just talked about. After we're finished those two short videos, then we'll spend a few minutes dropping our eggs to demonstrate it even further, right?